cell's battery's almost dead, you want to run glycolysis in the TCA cycle and electron transport. Alternatively, if you look at the other extreme, if you've already converted everything to ATP, you're going to shut that stuff down. So that's why you've got this downward curving system.
So that energy charge at the
Yeah, exactly.
well, up there it would be like
Unfortunately, this doesn't
like
have numbers, but
it's-
this is something that ranges between 0 and 1.
okay.
Okay, back to uncouplers. All of that we just talked about depends on there being an impermeable intermembrane system that can hold back the protons to keep the gradient intact. If you physically disrupt that by tears in the membrane, you lose the gradient, you lose ATP synthesis. Uncouplers do the same thing in a chemical sense. They're hydrophobic molecules that can dissolve in the membrane, but they've got one or more titratable groups on them. So it's got something that can pick up a proton, and then, because it's mostly lipophilic, it'll diffuse through the membrane, and if it gets exposed on the other side where the pH is high, well, it will give up that proton on the other side. So it provides a pathway for protons to move back into the matrix without going through this ATP synthesis machinery. There are many classic uncouplers. These are some famously used ones. We'll see their pictures here. This one is especially interesting, maybe to you guys, dinitrophenol. This is, the pink one is the titratable group. It can be an O- in some states or pick up a proton in the neutral, and it will move through the membrane, and if it's not acidic on the other side, it'll give up that proton. And because it's mostly hydrophobic, because of the benzene ring, it can flow back and forth across the membrane. It spends its life mostly dissolved in the membrane. So it will do this kind of shuttling of protons from one side to the other.